chapter 12, which gives us a chance to review linear regression, but also works in inference on whether or not we can prove that there's statistical evidence of a linear relationship for our data. So just like with any inference, statistical inference, you need to think through your conditions of whether or not that inference is appropriate or not. So first of all, you have to create your scatter plot, because if we recall, the only way to see if you have a linear relationship is to look at the relationship that you have graphed. So you actually will absolutely need to create a graph in order to see that it's linear. And if you have quantitative information where your x and your y are both numbers, then you have a possibility of doing linear regression. And so the question that we're going to be answering today with statistical inference is, does there really seem to be a linear relationship, or is that just something that appears to be happening by chance? So we're going to be looking for statistical evidence and either rejecting the null or failing to reject the null. We'll be creating confidence intervals and seeing if that slope, which the population slope will be beta sub 0. We'll see if that value of 0, if that's in our interval, then that would give us an indication that maybe there's not evidence of a linear relationship. And in a population, how much will this predicted value of y change for every increase of x units? That's our slope. And so we want to think about that margin of error, and that's our confidence intervals. Okay, so we're going to be looking at those things today. So for example, we looked at this example, Old Faithful Geyser, in chapter 3. We had scatter plot of the data, and here's that same scatter plot from chapter 3 with 222 recorded eruptions in 1 month. And the least squared regression line for this population data was added to the graph. It has a slope of 10.36 and a y-intercept of 33.97. So for this particular month, this was the true regression line. We know the true population regression line for this data. And so what we're going to do is, knowing this true line, let's compare what sample results would have shown in comparison to this true line. Now, if I was describing this line, I would absolutely need to talk about its form. Does it look linear? Does it look curved? If it's curved, we can't do linear regression, not until next unit, 12.2. We'll learn how to do it with curved data. We're going to have to transform it. Etc. What does it look like? The form, the direction. Is it positive going up, meaning like an increase in x means an increase in y? Is it negative? That's going down, so an increase in x is a decrease in y, and that's going to be related to your slope. And then you've got your strength, and for that we look at our R value. Remember, we have R values. They can be anywhere from a perfect positive relationship of 1 down to a perfect negative relationship of -1. There are no units on R. And that tells us the strength of it, and the closer we are to 1 is strong, and R equals 0, that's when we think there's no relationship based on the scatter anyway. So like, let's say, now now that we know the population, let's say we take a simple random sample of 20 eruptions. So pretending that you didn't know the true population, you just were going out there and did 20 eruptions, and you want to calculate your least squared regression line. Y hat, the predicted y, is equal to a plus bx for the sample data. How does the slope of the sample regression line, also called the estimated regression line, relate to the slope of the population regression line? So remember that our sample values are unbiased estimators of the population values. So I'm going to write the equation as a sample. I would have my y hat is equal to my a plus my bx, and that would be for a sample, but then there must be population symbols for this. So mu for the population, and then if you look on your, let's see, formula sheet, that they don't have it, but anyway, okay, mu for the population, and then a alpha in Greek is that symbol that we were using for our, our significance levels, but they're just not that creative in stats. They keep reusing symbols, so that's not, your type 1 error there, and this is not your type 2 error either, but it's capital B in the Greek letter system, beta. So don't get these confused with your errors. One and type 2 error. It's just a matter of that they just so happen to not be very creative, and these are the population symbols that they are going to use for this regression line. Now, so we could go out and take these samples, and so you can see someone went out and took a sample of 20 eruptions, and it's hard to see, but there are some blue dots on this graph, and those blue dots are the dots that represent the sample. And from that sample, they generated a slope and a y-intercept, a predicted equation. And then they have another predicted equation and another predicted equation. And so you can see that the slopes, as we expect with sample data, there is going to be some variation from the true value. Because in this situation, we actually know what the true population is. But we can see that there's a lot of variation from that true value, that true slope of the regression line of 10.36. Yeah, and so this pattern of variation in the slope can be described by a sampling distribution, just like with the means that we had and the proportions that we had in chapters 9 and 10 and all those. And so if we were to go and have that population of eruptions in the Fathom computer brain and go out and take samples of 20 and then put them back and take another sample of 20 and put them back and another sample of 20 and put them back, and every time you took out your sample of 20 you generated a slope, you can see that this approximate sampling distribution starts looking nearly normal. And so that's why we're going to be able to do significance tests about the slope. And this, because we had n equal to 20, it did not meet CLT, central limit theorem, but we are doing something that's involving means. but this slope inference involves means. And what does means involves? Which is T, which is robust. So if we can look at the graphs of the data, then even at low levels, we can do a T interval or a T test for this situation. Now, so we're going to go on to the next page where we're going to find out about how to describe or how to go through and do the conditions for regression inference for a slope. There's the acronym LINER to remember it. But just to say, like, when you're looking at your histogram, we do want to see that these B values are roughly symmetric and unimodal. We're going to do a normal probability plot of the sample regression line slopes, and we're going to see that it's going to come out closely normal, so we will be able to do some inference on that. So next page. Okay, so conditions for regression inference. So suppose we had n observations on an explanatory variable x and a response variable y. Our goal is to study or predict the behavior of y for given values of x. So first of all, we need to see that this thing is linear, because linear regression is not applicable. If it's not linear, then why are you doing linear regression? You know, that's basically there. So for this, if you're trying to prove that it's linear, you're going to want to look at its form. You're going to want to look at the direction. You're going to want to look at the strength to show that. Then you're going to want to show that it's independent. How did we do that? Generally speaking, with finite things, we're doing our 10% check. So there's that. That seems pretty familiar. Now, to prove that it's normal, what we're going to do is we're going to look at the residuals. Is the graph of the residuals look normal in the histogram? Right? Does it look normal in the histogram? We're going to be looking at that. And then equal variance, remember that scatter plot of the residuals, that we're going to want to have that chance scatter of the residuals. We're going to want to see it look like, remember it being like not systematically under over predicting. And then randomness, hopefully we have a simple random sample, because like that would be a well-designed experiment. And so this acronym that we're trying to do is LINER. So you're going to have these 5 pieces. Some of them have multiple parts to them, but you're going to have to come up with those before you can prove that you can do inference. So anyway, here's the summary of checking those conditions. And so let's go on to the next page. I'll let you read that, but we're going to go on to the next page and we're going to see someone has already made the graphs for us, thank God. And so we're going to see if we can prove the LINER acronym based on these graphs. Okay, so Miss Barrett's class did a variation of the helicopter experiment from page 738. The students were assigned 14 helicopters, and they assigned them randomly to these 5 drop heights: 152, 203, 254, 307, and 442 centimeters. Then the teams released these 70 helicopters in this predetermined random order. They measured the flight time in seconds, and then they used Minitab to go through and do their regression analysis of the data. So we have first of all, let's look at what kind of graph we have here, see if we can tell what kind of graph it is. What is it going to tell us based on, remember, we're looking for LINER, those things, so that we can prove that this regression analysis is going to work. Okay, so this looks like we have drop height, we have flight time. So this looks like a scatter plot of flight time versus drop height. That's what I see here. So what is that going to help me decide? It's going to help me decide the L. Do I see something that looks linear? So I need to look at its form. The form to me does seem to have a generally linear pattern increasing. So I would say that the form does appear to be linear. As you increase your drop height, your flight time seems to be linearly increasing. My direction is positive. My strength, now I don't know what R is. If I knew it, that would be kind of helpful, but I would say just on a gut, I'm just going to say moderate or strong, moderately strong maybe. And that's really just a guess, but it looks like it does have some kind of a relationship. Okay, so that's my L. So was I able to establish that it's linear? Yes. Okay, so now what kind of graph is this next one? This looks like it's a scatter plot of residuals versus drop height. Remember what a residual is? It's the residual would be it would be equal to your observed y minus predicted y. Okay, that's what the residual is. And so this one, to me, first of all, this confirms the L. Okay, that helps confirm this L, that it's a linear relationship, that there isn't some systematic problem, but it's especially helping me with the E, and that's equivariance. And so I would say that it looks like chance scatter equal scatter. And so that does look good. So that's definitely confirming my equivariance, E. Remember, it's LINER. So far, we've only got L and E done. So what kind of graph does this look like? This is a histogram of the residuals. So those are the same thing. I probably have them in L4 because I probably had observed Ys in L2 and predicted Ys in L3. So I probably have them in L4, and I did a graph of L4, and this looks like it is, I would say that is symmetric, bell-shaped, unimodal, just to give you some words there. It looks to me like that is going to support normalcy. So you're looking at your socks basically, shape, outlier, center, spread, and I don't see any outliers, especially from there. I mean, I could look at my box plot to check. but I don't see anything. And so this is going to support the N. That's the normalcy. And then just like establishing normalcy before with raw data, you look at the histogram, you look at the box plot for the outliers. They didn't give us a box plot, but to check outliers. But then we have our normal probability plot. And this one is normal probability plot of the residuals. Same data that was used for the histogram, probably in L4, I don't know. And this needs to be straight. Straight enough. So, and that is going to continue our check for normal. So we needed these two things to get our normal. We needed the two, those, and of course the box plot too. And those confirm that we have something normal. Now, the only thing I haven't seen is I haven't done the independent, and I haven't done the randomness. So let's, because right now, if I've got LINER, I have done E, I've done N, and I've done L. So let's do independence. Well, this is not a finite thing, these drops of these helicopters. You could keep dropping helicopters forever. So I would say that each helicopter drop is independent from the next helicopter drop. Next drop. But if you wanted to use the 70% or the 10%, so, you know, I think it'd be reasonable that you could have over 700 helicopter drops. And then random, they did say that they were doing they were going to randomly assign the helicopters, randomly assign the heights. In the testing. So I would say that was fulfilled. So that actually does indeed fulfill all the conditions for inference. So we can actually do inference about the regression model. But which kind are we going to do? Using T will be appropriate. And I mean, are we going to do an interval? Are we going to do a test? Well, let's continue and see. So don't be confused when you see that alpha and that beta, because they are not the type 1 and type 2 errors. In this case, we just couldn't think of different letters, but we have the conditions are met, so we can do the inference about this regression model. And the first step will be to estimate the unknown parameters. So if we calculate the least squares regression line, the slope B is the unbiased estimator of the population slope beta, and the y-intercept A will be our unbiased estimator of the population y-intercept alpha. And the remaining parameter is a standard deviation sigma, which describes the variability of the response y about the population regression line. So if we do a least squares regression line computed from the sample data, it'll estimate our population regression line, and that those residuals are going to estimate how much our y, our predicted y values, or predicted y values and the observed y values, how much do they vary from each other? Because how much did our observed y really vary from what the model is saying? So because sigma is a standard deviation of the responses about the population regression line, we can estimate it by the standard deviation of the residuals. So the standard deviation of the residuals will be, if you look on your formula sheet, it'll be the sum of the y minus the predicted y squared, add them up, and then divide by n minus 2. And why does it have n minus 2 instead of n minus 1? Because there is an unknown x and an unknown y. Unknown y. I'll just
So now we need the standard error for our slope. And so we take our standard deviation of the residuals and we divide that by the standard, and we find that using the formula from the formula sheet, the standard deviation of the residuals. And then we divide that by the standard deviation for our observed x values. And also divide by n minus 1. This formula can be found on our formula sheet on the second page of the formula sheet under the sampling distributions for simple linear regression. You can find all these formulas. Thankfully, though, the majority of the time you will have this information actually from computer output. So on the next page of notes, we actually can look at computer output, Minitab output, and see where would you have found the standard deviation of the residuals, and where would you have found the standard error of the slope on this paper. The Minitab output, this is a regression output for the flight time of our helicopters versus the drop height for our helicopters. So notice how I'm saying y first if I'm using the word versus. And so then when I look at the output, my y-intercept is negative 0.03761, and my slope is 0.0057244. And we can see that this output actually gives the standard error values. You probably won't be using the standard error for the y-intercept, but the very important standard error of the slope is 0.0002018. And so that'll be a very important number if you have to do inference on the slope. And of course, the standard error of the residuals is provided right next to the r squared, and that was 0.168181. So let's write the least squares regression line for this data. Our predicted flight time in seconds, notice how I'm putting a hat on it, will be negative 0.03761 plus 0.0057244 times the drop height, and that was in centimeters. And then let's review from previously interpreting our slope of this regression line in context. Make sure you use numbers for every increase of 1 centimeter of drop height. The flight time of the helicopter increases by 0.0057244 seconds. What is the real life meaning of our y-intercept? So that depends on what kind of domain you have for your data. And this y-intercept, where x is 0, is very far away from the rest of the x data that was used to make this. So the y-intercept means that when the drop height was 0 centimeters, the flight time of our helicopter will be negative 0.03761 seconds. This is a meaningless number because it's extrapolation. So this is extrapolation and meaningless. So now let's estimate the standard deviation of the flight times about the true regression line. What is this talking about? Standard deviation of the flight times, that's your standard deviation of your residuals. Like how much is it varying the predicted from the observed? That's your residuals. So the standard deviation of the residuals is from our output. We can find that 0.168181, and then we have to think about what units that would have. So the residuals is related to y. So what units would go with y? And that would be units of seconds, because y was describing the flight time. So on average, we expect our model to vary from the observed by about 0.168 seconds. Now the standard error of the slope, which thankfully was in the output, and that was 0.000218. And then what would the units be for the standard error of the slope? It would be the same as what the slope would have had, and slope is rise over run. So those units would have been seconds over centimeters. Now we can interpret the r squared. Now remember, r squared does not talk about your data varying because your data is whatever your data is. R squared is about how much of the variation in the model. "92.2% of the variation in the predicted flight time can be described by the model of flight time versus drop height, or can be described or accounted for by the model of drop height and flight time." And if we want to talk about the strength of the model and the direction, then we're talking about the R, the um, correlation coefficient. So we need to take that coefficient of determination, that R squared, which we can see in the output. We have to write it as a decimal so that we can then take a square root on that. And so this, and that whether or not we're going to call it positive or negative is going to be determined by the slope. Was this increasing or was it decreasing? That will match with your coefficient, correlation coefficient. So the square root of 0.922 is 0.9602, and I'm going to call that positive because I had a positive slope. So that R value will help us with the strength and the direction. Of course, remember that the form can only be determined by looking at your data. That's the only way to get the form. So the strength is strong with an R of 0.9602, and it's a positive direction. So now we're going on to constructing a confidence interval for slope. And you'll see that this process is extremely similar to confidence intervals for means, because we will be using t as well. And so we're trying to predict that population true regression line. And so if you look at the symbols, A has become alpha, B has become beta, but we're going to be doing an interval, so we need our sample slope. So we're actually using the sample value, and then we need to get a critical value. And since this is looking at means, then our critical value is going to be a t-value. And then we're going to need the standard deviation of our statistic. And in this case, our statistic is talking about slope. So our standard deviation of our statistic, which is our rise over run, is going to be our standard error of our slope. The degrees of freedom in this case, because slope was rise over run, that's why there's two inputs going into this. And that's why we would say, okay, there's our degrees of freedom is going to be n minus 2 because there's at least two unknown things out there that went into this calculation. So using our standard error of our slope, and we have our formula, which again is on our formula sheet, and we've been working with that already. We would then construct our interval. Now, in order to be able to do this, we would have to have gone through our conditions. our liner conditions, because in order to be able to do this inference, we need to be linear, independent, nearly normal, equivariance, and random. We're going to do a confidence interval for the least squared regression, for the slope of the least squared regression line. We're going to be using t. Our degrees of freedom is going to be our sample size minus 2. So we did 70 drops minus 2, 68 degrees of freedom. Our critical t value for a alpha of 0.05 divided by 2 with 68 degrees of freedom, and I use inverse t on my calculator to see what that value would be. And so bringing up the calculator so we can see that value. Negative 1.9954689, and so bring that over. Of course, I'll just call it positive. And don't forget, we had our estimate of our slope of 0.0057244 and our standard error of our slope, which actually came from our output. So we can put these pieces together to find the confidence interval for the what we're thinking is our best prediction of the values that the slope might be, the true slope. And so when we add this, we get a low level of 0.005322 and a high value of 0.00613. And we are predicting what's the population symbol, beta, because that would be the true slope of the linear regression line. So now let's write the, interpret it with 95% confidence, the interval from 0.00532 to 0.00613, and that would be, the units would be seconds per centimeters, captures the true interval for the true slope of the linear regression line describing helicopter flight time and drop height. And we can also see this calculation on our calculator, because the calculator has the intervals for slope on it. We just have to go down to its lin/reg t interval. And so very important that you're always backing up your calculations. And remember, we have our lists in L1 and L2. And just go down to calculate, and that would calculate the interval at the 95% confidence level. And you can even store your regression equation if you want to in there. So now we're going to do a t-test for the slope of the least squares regression line. And the interval that we were just doing relates to the two-tailed situation where the beta is not equal to the hypothesized value. And that's what the Minitab output as well is going to follow this interval, this two-tailed situation. You could do a test of greater than or less than, greater than being a positive slope, less than being a negative slope. And we have our t-test statistic with degrees of freedom of n minus 2. And if you look at the Minitab output, you can see that it actually gives the p-value in the output. In this case, the p-value was 0.000 because it was incredibly small. And this is actually the doubled p-value already. The Minitab output also gives the t-test statistic. I'll do a calculation so that you can confirm that that is the same t-value that you would have gotten by hand. Now, before we can do anything, we need our conditions of linear regression liner to be met, and we've already examined them for the helicopter. So we're going to do a t-test for the slope of the least squares regression line, following very much the t-tests for means that we have done previously. Our null hypothesis and our alternate hypothesis. Our null hypothesis is beta, and that would be the symbol for the population slope. That is equal to 0. The null hypothesis is basically saying that if beta is equal to 0, then we don't really have evidence of a linear relationship. So we are right now looking for evidence of our alternative hypothesis, which would be that we are finding evidence that beta is not 0, and that beta is in fact saying that there is some kind of a slope to the linear regression model. So we always test our null, but we're looking for evidence, just like in previous examples, we're looking for evidence of the alternative. In this case, our p-value, so our probability that our t-test statistic, in this case, we can see it in our output of 28.37. Let's verify that number by looking at the calculation of that t-test statistic, our statistic value minus our hypothesized value, which of course is 0 because you can see that in the null hypothesis, over our standard error for B, for slope. That t-test statistic is 28.37. So, and they've already doubled it in the Minitab output. So that already is, if you needed the positive or the negative, if you're testing an alternative that was only one-tailed, you need to divide that number in half. But we don't need to do that because we're doing a two-tailed. So since the p-value of 0 is less than alpha equal 0.05, we reject the null hypothesis, and there is significant evidence of a linear relationship between drop height in centimeters and flight time in seconds. The null hypothesis would be that there's not a linear relationship, but of course, we're looking for evidence of the alternative, and the alternative is saying that there is a linear relationship. Now let's look at an example where you have to do everything. Um, we have infants who cry easily, um, maybe more stimulated than others. Like, so is this fact that they're more in tune to the world, more able to be stimulated, is that a sign of their higher IQ? And so they snapped a rubber band on the sole of the foot of these babies and saw if the babies were crying. And then 3 years later, they examined these same babies to see what kind of IQ score they had. So they're trying to see, is there some kind of a relationship between these two things? We can't prove causation, but we're just seeing if there's a relationship. So they are saying that the X explanatory variable is the crying of the baby, and the response variable, which we'll put in L2, that will be our Y. That's going to be the IQ of the baby. And you would put this in your calculator and you draw a rough drawing with scale of your scatter plot to look for the linear condition. You would make a residuals plot to look for the equivariance condition, which also supports the linearity. You would make a histogram of your residuals and see if it was symmetrical, bell-shaped, and then check your normal probability plot. And that fulfills a nearly normal condition. And then, of course, looking at that this many children, let's see, is this 38 children? It's less than, the population of children. I'd say there's more than 380 children. And the randomness, I'm not convinced that it was completely random. I think this is going to describe the children who were in this particular study. But having the conditions for linear inference is met, then we're going to do a t-test for the slope of the linear regression line. Our null hypothesis is that there is no linear relationship. So beta being equal to 0. Our alternative hypothesis is that there is a linear relationship. And I think in this situation, you probably actually want to see, is there an increase in intelligence? So we're actually going to just look for a positive linear relationship for this situation. Our degrees of freedom will be, there were 38 children, so that is going to be 38 minus 2. So that gives us 36 degrees of freedom. So the t-test statistic now with our slope statistic minus our population beta and the standard error of the slope we got a slope of we got a t-test statistic of 3.07 right out of the Minitab output. They gave us that. And so the probability that our value is going to go above that is really half of the p-value that they gave in the output, because they gave 0.004. But remember that Minitab is for a two-tailed situation, so we need to divide that in two and we get 0.002. So the probability that our t will go above a 3.07 gives us a p-value of 0.002. Let's use an alpha. They didn't give one, so we'll use an alpha of 0.05. So since the p-value of 0.002 is less than alpha equal 0.05, we reject the null hypothesis, and there is significant evidence of a positive linear relationship between crying counts and the IQ for this population of infants. And I would definitely use my calculator and do the lin-reg t-test on the calculator, and verify all of these numbers that you can get them with the calculator. So one last example, and this example is in the book, but we can look at how using a calculator can really be helpful. So I've entered this data into L1 and L2. This is for fidgeting and calorie burning. So having entered that data into L1 and L2, I would check my plots. So I'm just going to do that kind of quickly to see if the conditions for inference are met. And I do see that it looks linear, decreasing from my scatter plot. So that is good. That's meeting the L condition of liner. I need to put need to get the linear regression equation so that I can put the predicted values into my calculator. So running the linear regression, this is the old software, so that's why I have to enter them in separately. At a 0.779 R value, I would say that's moderately strong. Now I can put in my slope, which is negative 0.003441487, and my y-intercept 3.5051222916. I can put those into the calculator, and I'm just quickly drawing these graphs. Feel free to fast forward through some of this, but I'm just drawing, and notice how I'm putting a scale, so that if you were doing this in your mini quiz or in a test situation, the person would know what you were looking at. So continuing this process of checking the conditions, I've got to put the predicted values into L3. So entering in the equation for the linear regression model, negative 0.00344148 times my L1 values plus the y-intercept of 3.5051229116, using a lot of decimals to avoid rounding errors. But so now I have my predicted values. Now, how far off are these predicted values? Let's put that in L4. Those are our residuals. So L2 minus L3. And now we have our residuals. So this is how far off on average we find that our model is. Well, that would be the standard error of the residuals, be how far off on average. But so now we can go and look at these residuals to see if we have our equivariance, to see if we have the nearly normal condition. So L1 versus L4, and I'm going to have to zoom stat to be able to see if I have my equivariance, and I would say I do have equivariance. And when I draw this on paper, I'll want to include a rough scale of this. So you may go in and look at what some of the values are to see a rough scale. So we're meeting the equivariance. Looks something like this. The scale probably was up to 1 and down to a -1. Now let's check the nearly normal condition. So beginning with the histogram to see if we have something that looks symmetrical bell shape. This is with the L4 list because we're doing this histogram for the residuals. Again, we're going to have to zoom stat, and I would say that this looks symmetrical. There's a little bit of a gap there, but I don't think that's enough to be an outlier. And of course, the fast way to confirm that would be to use our box plot. And so by glancing at that, we can see that there's no outlier according to the 1.5 IQR rule. So that's supportive of our being nearly normal. However, we always check our normal probability plot, that being a very powerful way to assess normalcy. We're looking for straightness in the normal probability plot, again using our residuals, and I'm zoom stat again, and this looks very good. It looks approximately straight enough that I think that that is more evidence that we have fulfilled the normal condition. So I'm just going to quickly draw a rough histogram, and I'll just say that there were no outliers. And it was roughly symmetrical. And our normal probability plot, again, we try to do a little drawing. I haven't done a good job with putting the scale, but you would want to have a scale. That's roughly straight enough. And then, of course, we need to have independence as well as randomness, just adding some scales to these things. Randomness was given in the problem. Independent because this number of people is less than 10% of the population value. Just looking back to see if I can see, there were 16 healthy adults, so I would say that there's more than 160 in the population. So the conditions for inference are met. We can do a t interval for the slope of the least squared regression line, and we can do a t-test for the slope of the least squared regression line. And I would use my calculator, especially when you have the data in your calculator. I would use the calculator to do your ln-reg t-interval and your ln-reg t-test, and then you'll know that you have the right answers, and you just have to show supporting work on your paper. So let's start with the interval, and we'll calculate the t-interval. And there it is, ln-reg t-interval. So I select that, and I'm going to go with the 95% confidence level because they didn't specify a different level. And if you wanted to store the regression equation, you'd use vars function y, and you could store the equation there. And there you have it. That's the interval for this situation. They give you the prediction of slope. They give you the degrees of freedom. They give you S. And remember, that's the standard deviation of the residuals. They gave us the confidence interval for the slope. And since 0 is not in that interval, that is supporting, I bet that we will get a conclusion that there is evidence of a linear relationship. And now to do the linear regression t-test, let's go down to ln-reg t-test. And we have our data in L1 and in L2. And so now we just have to decide what our hypothesis was. If we are looking for beta being not equal to 0, do we want it to be less than, greater than? We can even store our linear regression equation. And we're going to be putting by hitting vars function y vars. I'm going to pick y1. I'm going to store my linear regression equation in my calculator. And then I can hit calculate, and I'm going to do the two-tailed situation because I'm relating this to the interval. And so then my t-test statistic was a negative 4.6418. My p-value of that happening is 3.81 times 10 to the negative 4 with 14 degrees of freedom. And then you can see what my a was. That's the y-intercept. If you look at the y equals a plus bx. I have my slope as well. I have my standard error of the residuals. I have my r squared. I have my r. So I have a lot of information that came out of that lin-reg t-test that I can then do. And this, because that p-value is so small, that is evidence that I would reject my null, and I have evidence of a linear relationship. That was supported by our interval, wasn't it? Because our interval also did not have 0 captured by the interval or between the intervals. So writing my predicted equation with y being the fat gain in kilogram and x being the change in calories burned by our our NEA. So predicted y will be negative 0.003441487 x, that was a slope, plus 3.5051222916. I have my slope with degrees of freedom of 14. My critical t value for a 0.05 divided by 2 with 14 degrees of freedom is, let's look at this with the inverse t. We can see what it was. Point 0.025 comma 14, negative 2.1448 basically. So what if you were trying to get the standard error for your slope by hand? You would need to use the formula from the formula sheet, the standard deviation of the residuals divided by the standard deviation of x times the square root of n minus 1. And so you would then, if you were going to try to do your standard deviation of your residuals, knowing that that is actually based on n minus 2, you can't just do the standard deviation of your L4 list. You actually need to find out what is the sum of your residuals, each of them squared, and then that is going to get divided by n minus 2, and then you're going to take the square root of that. Now, if we could get that value, we would have the numerator for our standard error of our slope equation. So and I'd also need my standard deviation for my x values. So I'm just filling in some of the information I do have. So let's go to the calculator and let's see what we can calculate to get the sum of our squared residuals. Now my residuals are in L4, and if I want to square them, I could square them in L5. And now the fast way to add up this L5 list is to calc 1 var stat L5. And I can see that the sum of the x values, because remember my x values are the squares, is 7.66335, etc. I could have just as easily have calculated the 1 var stats on my L4, but if I did it this way, then I'd look at the third row down and you can see it's the same exact number, 7.66335. And that's because in that list, it took the sum of all of the x squareds and added them up. So that's the sum of my squareds. I now need to take that number and I need to divide that number by the n minus 2, which is 14. Okay, now I have the number that I need to take the square root of, and this will be the standard deviation of my residuals. There's the standard deviation of my residuals, 0.7398528,737. So I found one of the inputs that I need to get my standard error for my slope. I also need the standard deviation for my observed x values. So by looking at L1, I get 257.6567484. Let's take both of these numbers and put them into the standard error of the slope equation. Didn't leave a lot of room for myself, but I'll try to squeeze these numbers in. There's my standard error of my residuals. Standard deviation of the observed x values. My standard error for my slope when I divide all this out. Point 0.0074114. And so I'm just writing down some of these numbers that I had. And of course, that number, that standard error of the slope, is important for our interval calculation because I'm going to need my slope. I'm going to add and subtract my critical t value and my standard error of the slope that I just found. So putting those numbers all together, and I'll get the exact same interval that I got using my ln-reg t interval. So to write our interval, which matches what we got in the ln-reg t interval, negative 0.005 up to negative 0.0019, and with 95% confidence, the interval from, anyway, that captures the true linear regression line. So now for the t-test for the slope of the linear regression, if our null hypothesis is that there's no linear relationship, so beta is equal to 0, and we're testing the alternative hypothesis, testing for evidence of the alternative hypothesis where beta is not equal to 0. So our slope minus our hypothesized value over our standard error over our slope. Thankfully, we've already got that number. We're going to take our slope and subtract 0, because that was what we said the null hypothesis was, and divide by our standard error of our slope. Gives us a t-test statistic, which we already know because we did the ln-reg t-test. This value is 4.641. And now we're going to find the p-value, which is the probability that our t will go above this value. And then, of course, we will need to double it because we are doing a two-tailed situation. The degrees of freedom is still 14. (1.90 times 10 to the negative 4). Got to double this. So this is looking like significant evidence that we will reject the null hypothesis. Basically 3.8 times 10 to the negative 4. And this shows us that we have evidence of a linear relationship for our